Welcome to geology, everybody. Metamorphic rock time. So, if we go back to our three geologists sitting around the campfire arguing about why theirs is the coolest, the metamorphic person is going to say that their rocks were like created by geological processes, maybe more than the others, by tectonic process, certainly more than the other. Think of all the heat and pressure it took and all the time it took to very slowly form these rocks in these extreme conditions. And then all the time it took for the top to erode away for them to be exposed here at the surface of the earth. And it also allows you to see further back into Earth's history than you might be able to with sedimentary. Sedimentary is great for, letting us know the last half a billion years of life's history, but sedimentary rocks older than that tend, because they're softer, to erode away a lot more easily, which means we can't identify them anymore, right? If we want to go way back in Earth's history, it's going to be metamorphic rocks that are still around because they're hard. They're so resistant to weathering and erosion. So what are they? What do we do? I didn't do a separate note sheet for this one. I think we'll just kind of look at the chapter and call it good. There's some pretty good diagrams here, with the exception of the rock cycle. That's not in here. Let me pop that up quick. So going back to chapter 6 here, it is again. And the reason I like to pop this one up specifically, it's great, is that they show that you need this you need this deep heat and pressure to form these. And then we also are going to need some process to go through uplift to bring them back up towards the surface where we're able to see them, which means shedding off those upper layers of rock. So any of the three can turn into metamorphic rock: sedimentary under heat and pressure, igneous under heat and pressure, or even metamorphic under further developing heat and pressure, or multiple episodes. What your book does do, remember this when we went back to when we're talking about plate boundaries. Here's my video that you should have watched back in that segment of the course, with India and Asia ramming into each other, creating the Himalaya Mountains. And at the top of the Himalaya Mountains are actually made of sedimentary rock. That idea that's everything you can say about geology in a sentence, that the highest points on Earth are made from rock that form below sea level. So that's happening today. Those mountains are probably going to get a little bit taller today, also wear down a little bit, but the net is a gain. What about way down deep here in the core of the mountains, where there's the pressure of two continents ramming into each other? Also today, way down there, we're forming these metamorphic rocks. Not so hot that it melts, because then you're talking igneous. Enough pressure, though, to change the nature of the rock themselves. So if we could jump into a time machine and go forward hundreds of millions of years and look for this rock, the top by that point is going to be all eroded away. And if this is kind of tectonically settled and events have gone elsewhere, like they have in the Appalachians, if it erodes away, we're going to be able to see deeper down into the core of these mountains, to the rock that is developing, thanks to erosion. Your book actually does do a decent shot at that, but it's way down here. I just saw it. That one. So take where crust is ramming into itself, and you'll develop, we'll talk about this, like these ideas of these rocks in just a minute. Blow this up a little bit. But take this and cut the top off, because presently you're not forming any more metamorphic rocks near the surface. Once later on in Earth's history, when the top is gone, we'll be able to see those. And there's the diagram that does a good job of that. So again, during mountain building presently, after all of that's gone, there's also some isostatic rebound. This bounces back up, which will allow us to see the deeper layers of metamorphic rock. All right, so what should we look for? Let's start with we already started, right? Let's take a next step with foliated versus non-foliated, which you're going to look at right down here. And whether we get into this foliated versus non-foliated thing has to do with the conditions when this formed. What did it come from? What was its parent rock? And what environment was it in to go through this metamorphism? How high did the temperature get? What was in there at the beginning? And that's going to really determine what it looks like. And it gets complicated because you can take different rocks, put them in the same scenarios, and get different metamorphic rocks. Or you can take the same rock and put it in two different metamorphic scenarios and get two different looking rocks, and it can turn into a real mess and be complicated. But a lot of that we'll save for more advanced geology courses. So what is going on with the pressure? Is it coming in uniform and compressing? And this is a neat little diagram that I do with just clay. If you take clay cylinders and lay them down and just mush, you get that. Maybe this does a good visual on why these rocks are harder and more resistant to weathering. You're taking those minerals that may be packed to some degree and through that heat and pressure fusing them together a lot tighter, reducing any pore space and then also forming new minerals as this happens, or shear, which can give you these big bent things. And we've seen images like that when we did geologic time. And what another thing that the geologists might say that's neat is that new minerals are, I don't want to say invented, but created within the rock due to this heat and pressure. Take whatever the minerals are in a rock and put them under that much, and especially if you include fluids, you can have on an atomic scale, it's crazy. You can have on an atomic scale different combinations within those atoms and within those minerals and lead to forming brand new minerals out of that over very long periods of time, of course. So foliation versus non-foliated. This is what we're going to look at here. So take this pre-existing igneous rock, put it under pressure, and I think they did it here just by using like a photo editor and mushing, right? But it gives you the point. What happens if you squish it is that the grains themselves are going to start to get aligned. All right, so some of the foliated ones we'll see are where are we at? Slate, phyllites, schist, and gneiss. Those are going to be the kind of the main ones that we look at, right? So check out the little bit on each of those, and then what I wanted to do here was to find this diagram, which I just looked up, is down on page 20. This looks like a train wreck, but don't panic. It's not too bad. What this does is it graphically shows us with increasing depth going down from the surface. That's why the y-axis here might look like it's upside down. They do it with going up in depth, which is like going down, right? So going down this many kilometers, what happens is the temperature goes up in that direction. So what we got is to the far left, this just doesn't happen. You can't get that deep within the earth without simultaneously getting hotter. So this just kind of doesn't happen over here, right? The main set of those rocks we just mentioned, slate, phyllite, schist, and gneiss, they're going to happen over increasing heat and pressure as you get deeper and deeper and deeper within the earth in the different environments that we'll look at in just a moment. This red line right here is going to be basically, we can ignore everything that's past this line for purposes of the test that I'll give. Past this line, you're talking about melts. So hopefully in your head that triggers, hey, that's igneous rocks, that's something different. So we're surfing the narrow area here between conditions that just plain don't exist and where rocks melt. Where do we get enough heat and pressure to create these, but not so much that it melts? And maybe even right towards the top here, the tippy, right in the end of this, we could talk about that being like your sedimentary environment. You need a little bit of pressure, but not too much. Working down from there, like the main set of your foliated igneous rocks, with increasing heat and pressure, increasing heat and pressure, increasing heat and pressure, increasing heat and pressure, goes slate, phyllite, schist, and gneiss. So check out that little bit back on those pages we were just on those specific types right there. They each got a little blurb. Sorry. There you go. Page 8. Slate, phyllite, schist, and gneiss. All right, back to 20. What about if we're up here close to the top? What that would mean is that we're getting way up there in temperature, but not really getting deep enough to get a ton of pressure on it. And that's going to be something we call contact metamorphism. And again, when we do our like types of metamorphism, we'll check those in a sec. And then the ones that come down really hard over here are that you're getting very deep very quickly before you have the chance to heat up a ton. And that's going to be due to subduction zones. If you go back and remember subduction zones like oceanic continental or oceanic where crust is being sucked down underneath. If it goes down that quick before it has the chance to heat up, you can form those. Those are reasonably rare to find towards the surface because what that would entail is that subduction took place and then stopped, enough that it didn't go down and melt, that it at one point got brought back up to the surface. They're fairly rare to spot on the surface of the Earth versus these others that are much more common. So yeah, let's look at the non-foliated real quick, then we'll do the environments and get you out of here. Which we'll go back to marbles and quartzites. So where you don't get the alignment, like let's step back and just say what is this? What is the main difference with the foliated? It's alignments of minerals, easy to see with gneiss. The significant amount of heat and pressure creates these big bands of minerals. A little trickier, but not impossible to see with schist and phyllite. You can see it here. Alignments somehow of minerals are visible within the rock. That's the definition of what foliated is, versus non-foliated from some pressure and some the state of some minerals as the pre-existing rock would be, yes, that's metamorphic, but I don't see anything in there to indicate an alignment of minerals. Quartzite, same idea. Okay, there's one really good, this guy right here. So check this one out. Maybe have this handy on page 12 of the PDF version. This says, what's your protolith? Like a prototype is an early form of a car, right? Protolith, same idea. Like what is the pre-existing lith? Generally, like lithos goes with rock types, right? So what's your pre-existing, your early form of those rocks? And then where on that chart we just checked out on 20 have we gone from low up to very high grade metamorphism? And again, that's why I said this stuff can get complicated. Igneous is easy because the dark ones are this, the light ones are this, the coarse ones are this, the fine ones are this. Metamorphic's a lot more of a mess because, again, different rocks can create more similar rocks under heat and pressure, or the two similar rocks can go down two different paths. It gets messy, it gets sticky. So check that out and have it handy. Maybe it'll come. Excuse me. All right, so let's wrap it up briefly with the types of metamorphism. And this will be another place where I say, hey, for our test here to 100 level, let's just break this down to a couple. But if you're a major, you probably want to start to get this down, to get the more intricate ones down, right? So let's just focus on really the regional. That's what we've talked about with like what's going on in Everest right now. These two paragraphs are great. They're very concise. They say exactly what's going on. And again, there's that diagram that we checked out. Regional region, right? A huge area is presently being produced of metamorphic rocks. They're in the bones in the center of the Himalaya mountains with sedimentary rocks way on top. I'm not going to worry about the seafloor one for our test. Majors, check it out. Subduction zone ones, like I mentioned that with the blue schists, that yes, this happens and they're forming right now in subduction zones. I would expect to see this. I mean, if you're really like thinking about this course, with all the units together, right? Maybe we can recognize this as like what's going on underneath South America. Subduction on the west coast of South America. Subduction. So rocks like that are forming now. The problem is that generally they're going to continue to get subducted until they melt and feed those volcanoes. Occasionally, to different tectonic situations, put a pause on that, and those have made it to the surface fairly rarely. But I would say the two we should really think about at a 100 level course is the regionals we mentioned, and this one, contact. Contact is going to be more like heat only instead of the heat and the pressure. Take some place where magma is working its way up towards the crust for various reasons. Think of the dikes and sills we looked at with the igneous rocks. That's hot, right? It's melted. Excuse me. Not feeling great today. It's hot. It's melted rock after all. So the rock that it contacts, first off, it might melt its way through, in which case that's melted rock. We're talking igneous. But other places, it will just contact and slightly alter the minerals within the rock that heat contacts. So it's not the same as the unmetamorphosed rock surrounding it, but it's not the igneous that's inside of it. It's like a ribbon around it, an aura around it of contact metamorphic rock. All right. That should just about do it. And there's another good diagram of, okay, we got the subduction, the melting that comes up, and where that contacts would be contact metamorphic rock. Shock's kind of neat, but not common enough for us really to worry about too much. So check out we did that. Check out the bottom here, a couple of questions, see what pops up, and we'll be in touch with you soon. Take care.